Hi everyone and welcome back. So how does a transformer understand and translates a language? It all starts with input representations. But how does a computer understand words like biryani, Hyderabadi or chicken? So for example, if you have a task, I like eating chicken biryani, Hyderabad. Okay, now I'm talking like LSTMs. But if I have tasks, I like eating Hyderabadi chicken biryani, and you want to convert this sentence into Hindi, saying मुझे हैदराबादी chicken biryani खाना बहुत पसंद है. So how exactly do transformers do this, right? Because they don't understand words like biryani or khana directly. So how do they process the text? Today, we'll break down the first steps of transformers, which is inputs, your input embedding, and the positional encodings. And to make it real, we'll use a delicious example where we'll say, where I want to translate, I like eating chicken, Hyderabadi chicken biryani into Hindi, saying, मुझे chicken biryani खाना बहुत पसंद है. So let's get started. Now, the first step that any transformer model does is to convert the text into a format that could be understood mathematically. Because we understand words, but the transformer or the machine understands only numbers. So this is what happens where you give the input, and this is what happens in the input embedding. So the first step that happens is tokenization. Now, what exactly is tokenization? Tokenization is nothing but, let me just pull you to this particular location. So this is what happens inside a input embedding. You get your input text, and after getting your input text, something like I like eating chicken biryani, you first tokenize it. Now, exactly is a tokenization? You break your words into tokens. Depending on the model, we might use a word level or a sub-word level or even character level tokens. Over here, we'll use sub-word level tokens. Now, example over here is tokenization of our sentences using, sorry, so the example over here is you have, I like eating chicken biryani, and then you tokenize it into something like I like eating Hyderabadi chicken biryani. And then over here, what you see CLS and SEP is basically you are indicating, you have a particular, you are basically indicating that this is start of a sentence and this is basically end of your sentence. Now, after tokenizing it, you will fetch the position of each of the words in the embeddings and then assign it. Okay. So now, what exactly does this mean? Instead of the words, we are working with tokens, right? And these tokens are mapped with a unique identity in a vocabulary. Each token is taken as a number. If you remember, so we did something similar in word embeddings, word to vec in embeddings, where we had something similar in word to vec, doc to vec, glove, and those kind of embeddings, right? You can refer back to that video, it's in the playlist. So now each token is now a number, right? And this is what the transformer actually processes. Now, now that we have the tokens, the next challenge is how do we represent these meanings, right? And this is where the word embeddings comes into picture. Instead of just using plain numbers, we map each token to a high dimensional vectors that captures its semantic. So for example, the biryani should be something which should be very close to your food in the vector space. Now, I understand that we have already discussed this before, but just a quick recap, what we are doing is we are trying to understand the word embedding in action, where the word biryani should be very close to food in the space, and the word like should be very close to love than the hate itself, right? So each token gets converted into a dense numeric representation known as embedding vector. And this is the position of those of the embeddings of that particular vector, of that particular token in the entire word embedding itself that you're using, right? Now, there can be different word embeddings that you can use over here. But the key benefit of the embeddings over here is that the embeddings capture the meaning and the relations between the words across, even across languages. Now, over here, what you will see is the position, the 101, 283, 238, and 315, and 369, etc. These will represent the position of embedding of this, the position of the embedding of this particular word in the entire embedding vector space. So for example, if we are using something like word to vec, then the embedding of the word I would be at 238th position, right? And then the step 4 would be you fetch the embeddings from the position in the vector space. For example, at 1 1, you will have your embedding something like this. So this CLS will now be represented by this particular vector. Similarly, I would be represented by this particular vector, like by this vector, eating by this, and so on. You get the idea, right? So now once we have converted your input text into embeddings, something like this, you will next move to your position vectors. But some fun facts over here that the BERT model has a vocabulary size of around 30,522 tokens, and the GPT-3 vocabulary size was around 50,257 tokens. So these many tokens were, so the GPT-3 was trained on 50,000 plus tokens, and the BERT was trained on around 30,000 plus tokens, similar to these kind of tokens, right? Now, once this is what will happen in your input embeddings. Now, let's try to understand the word embedding itself, right? And I know we have covered it, but we'll try to understand what exactly was word embedding, and how does it fit into the picture over here. So the word embedding is nothing but representation of the words king, queen, man, woman, hate, cat, dog, kitten, whatever, etc. in a multi-dimensional space, vector space. Now the Google Word to Vec uses 300 dimension. Glove uses around 300 dimension. I don't know. I have written n dimensions over here. Yeah, because I think Glove has different vectors, different vector representations, which has different dimensions. The BERT uses around 768, and GPT uses somewhere around 12,228 dimensions. So now what exactly are these dimensions? These dimensions could be represented, will have numbers such as something over here. Now the cat, now this is a very condensed form where you just have around 7 dimensions, but you will have sort of 300 dimensions representing a particular word or a particular token in many of the embedding cases, right? Now, suppose you have cat, which is represented by, now this is just an example that I'm giving over here, where you have cat, and the cat is represented by, say, this particular dimension. Similarly, kitten, dog, house, men, women, king, queen, etc. They are basically represented by these embeddings, by these vectors, vector embeddings, and each of the value that is there in this particular vector embedding, each of this number can represent sort of a characteristic of that particular entity that is being represented. So for example, the cat, how well, now this is just an example, but it doesn't actually have living being or human or gender kind of representation. It might understand it something very differently, but ultimately you can consider these embeddings or these vectors as features, or these particular float points as features. So you can have a cat, and then how exactly is it in living being. So it classifies something as 0.6 in the living being itself. And then you can have something like how human the cat is, what is the gender of the cat, then royalty, verb, plural, how exactly is can you define a cat by giving weightage to each of these characteristics. And that's how you have different characteristics for different weightage for different words or tokens inside the embedding, and you try to represent it, right? Now the beauty of these embeddings, as we had discussed previously, is that when you do something like man plus king minus women, you'll get your embedding something close to the embeddings of queen. So that means it is capturing sort of a meaningful representation, and it is not capturing just gibberish. So this was about the word embeddings and the representation which happens inside your input embedding. After the input embedding, these words then goes, or these embeddings, word embeddings, goes into positional encoding. Now let's try to understand what exactly is happening in this positional embeddings. So in the positional encoding, let's try to understand it with an example. Suppose that you have, she was a perfect match for me, and you have something like, can you light the candle with this matchbox? Now the embeddings that are coming from your this word embedding or this input embeddings, the embeddings of match would be the same, right? Something like this. The embeddings of the match would be the same. But if you look at this particular example, the match over here and the match over here have completely different meanings. So there should be some particular sense that should be added to this particular match, so that you can differentiate this match from the matchbox itself. I'll give you another example where you have something like Nashit likes to eat dash, and you have another example which says Nashit eat your dash. Now again, in this too, you will understand the position of the eat itself gives you a different context to the meanings. So the position of the eat is giving you a different context and is completely changing your sentence itself. So this is where you will have positional encoding. This is where you will have your positional encoding layer, which will try to give it an essence or a meaning of since transformers don't have the built-in sense of order, we add special position encoding vector to each word embedding. Now, mathematically, how do you compute it? It's computed using sine and cosine functions, something like this. This is the formula that we use. Okay, so now the encoding is added to the word embedding so that the model can differentiate by the positions. Now here I'll just pause for you to look at the formula and understand it better. The POS is the position of the word in the sequence itself. This starts from 0. Ith is the dimensional index of the embedding itself, the word embedding that we are using. And then D is your total dimension of the word embedding. So when you put these into this particular formula, either this one or this one, you will get your positional embeddings. Now, this encoding is then added to the word vector so that the model can differentiate between the positions. Now, how exactly does the positional encoding works? We'll try to understand it. Now, how exactly does the positional encoding works? If at the if I is at the position 1, a different encoding is given than the biryani at position 6. This ensures that the transformer knows who is the subject, object, or an action. So let's try to bring it all together, shall we? The input sentence, I like eating biryani, gets tokenized to I like eating Hyderabadi biryani, which we saw over here, and then from there it gets converted into embeddings where each token is getting converted into dense vector, and then each of these vector is then added to maintain a word order by the positional encodings that we learned over here. Okay, now each of these words which are coming out of the positional encodings is mathematically rich representation of meanings plus positions, and this representation is then fed into the transformers encoder over here, right? Inside this transformers encoder will have self attention and multi-head attention, which would come into play, which we will break down in the next lecture. So today we have learned about the transformers architecture, the beginning of the transformer architecture, on how the words are taken and the text is converted into numerical representation using tokenization, embedding, and positional encoding. Now, I want to hear from you. I want you to let me know what's your favorite multilingual phrase that changes meanings based upon the word order. Drop it in the comments and share it with someone who might love it. Thank you.